Can I start? Good afternoon, professors and team members and the audience. I'm Jim Kim from Hanyoungwe국고등학교, and I want to present on the question number 2 caught in the air. The question is stated as, when a piece of thread with a small mass attached to its end is rolled around, a distinct noise is emitted. So I highlight some keywords. First is a piece of thread. We define the piece of thread as a thread which has enough tension and the even surface to make the sound. And also, we define the small mass. We define the small mass as the object which would fix one end of the string, therefore making the sounding wave. So we have to study the origin of this noise and the relevant parameters. And this is the full chart of my presentation. First, in order to observe the sound generated by the system, we want to focus on the two most important factors of the sound, the volume and the pitch. Then, we will examine the three theories on the generation of the sound, the sending wave, the counter vortex, and the vortex behind the spherical objects. Then move on to the experiment. I will examine the volume and the pitch of the generated sound with its three parameters. Then move on to the conclusion about the relationship between the sound and the conclusion. So the motivation for my presentation is that the main source of sound will be the standing wave, which is made when the thread is vibrating. And additional sound will be generated from the vortex behind the thread and the small mass. And the vibration of the air particles around the thread and the small mass will make the resonance with the standing wave. So in order to see the combined and the individual influence of these three theories, we set the parameters as follows. First is the thickness of the thread, and second is the size of the ball, and third is the velocity of the system. So move on to my first theory about the standing wave. Standing waves are made through the interference of the incident wave and the reflected wave when the both ends are closed in my experiments. So the fundamental frequency of the standing wave could be expressed as follows, and T is a tension. So from this we could derive the equation for the harmonic frequencies of the standing wave. Since in our experiments, the ball and the thread are doing the horizontal circular motion, the tension equals the centripetal force. Therefore, the tension could be expressed as the R over mv squared. So from this part, we could get one of our parameters in the experiment, the angular velocity. So move on to the counter vortex. Counter vortex is a periodic swinging vortex caused by the cylindrical bodies. However, it does not occur for all cylinders. It only occurs for the cylinders above the Reynolds number of 90, and the Reynolds number is the number representing the ratio of the inertial forces to viscous forces, and I will explain it later. So the counter vortex is the vortex between the moving fluid and the steady object. However, our question is asking the opposite, the moving object disrupting the steady air. However, the equations related to the counter vortex could be applied to our question, since both the fluid and the air in the same reference frame, we could consider that both the air and the object are moving in a relative sense. So as our assumption, the V's in the equations in our presentation would be the string moving velocity instead of the air flow velocity. So when the air flows towards the thread, the airflow has to go over the thread, therefore the airflow has to be separated. So due to this airflow separation, there will be the unsteady and the recirculating vortex behind the thread, and this is the counter vortex. So during this process, at the point when the counter vortex frequency equals the standing wave harmonic frequencies, there will be the resonance. So we will mainly hear this resonating sound. So I explained the relation of the counter vortex and the standing wave and the resulting sound. So move on to my final theory about the vortex behind the spherical objects. The mechanism for the vortex made behind the spherical objects is similar to counter vortex. The terminal flow would occur at the back of like the ball shape at the high Reynolds number. So when the air flows towards the ball, the airflow has to go over the ball. So due to this airflow separation, there will be the vortex behind the ball. So there will be the resonance when the vortex shedding frequency equals the thread standing wave frequencies, there will be the resonance. So before moving on, first we have to prove the occurrence of the counter vortex and the vortex behind the ball in our experiments. So this equation for the Reynolds number, The V in the above is the velocity of the flow upstream of the cylinder. However, as our assumption said, it would be the angular velocity of the thread. And the D is the diameter of the thread. The mu in the below is the kinematic viscosity of the air. So by putting these values to our experiment, we will get the Reynolds number for our experiment, which is 4,000, which means for x is 90, the minimum required number for the occurrence of the common vortex. So this is the general experiment setup for my experiment. We use the wire as a thread and fixes one end to the motor axis and another end to the strap ball. And we use the strap ball as a small mass attached to the thread because it is easy to change the mass and the size of the ball. Then we use the electric thread motor to give a constant values of angular velocities and also make the horizontal circular motion of the ball. And right over the motor axis, there is a sensor to give an equal distance from all points of the circular paths of the ball, therefore enabling to measure the sound, the volume, and the pitch of the generated sound and consistency. So this is how the ball and the thread all wheeled around in my experiment. As you can see, the ball is doing the horizontal circular motion, and while the system is doing this motion, the sound will be generated, and we will measure this sound. By varying the independent variables of the angular velocity and the diameter of the thread and the diameter of the ball, we could obtain how the frequency and the volume of the sound change according to these parameters. So the method I use to measure and analyze the frequency is the FFT, the fast Fourier transform with the aid of the computer program SIA. As you can see, the fundamental resonant frequency of the sending wave is quite obvious, as you can see. So move on to my first experiment about the thickness of the thread. I use the same type of wire with different diameters. The thinnest one with 0.5 centimeters and the thickest one with 0.50 centimeters. So this is how the frequency changes according to the diameter of the thread. As you can see, in the encircled region, the frequency gets decreased when we increase the diameter of the thread. So as thread's diameter gets, and for the analysis of the results, for the thread with a large diameter, it takes more time for the airflow to go over the thread. Therefore, the frequency would have an inversely proportional relationship to the diameter of the thread, and this could be expressed as follows, and this is the equation for the vortex shedding frequencies. So we could get a conclusion that the diameter of the thread is inversely proportional to the frequency of the generated sound. And this is the graph about the sound intensity. As you can see, there is no much change in the sound level when we change the diameter of the thread. So, first, the energy is formed when we wheel the motor. And some of the motor's energy will be transformed to the sound energy, and we will mainly hear the sound. So, since we wheel the energy given to the motor by the electricity is constant when we do not change the angular velocity of the motor, there will be no change in the sound energy that will be transformed from the motor's kinetic energy. So we could get a conclusion that there will be no difference in the sound intensity. So move on to my second experiment about the size of the object. So independent variable in this part is a spherical ball with a diameter of 3, 4, 5, 6, 7 centimeters. So from the experiment 1, we found out that these peaks are actually from the influence of the thread. However, we were kind of wondering about, so where these below peaks are actually come from? And we could get the answer for this question from the experiment 2, that these below peaks are actually from the influence of the ball. So this is the frequency graph. When you change the diameter of the ball, the above peaks do not change. However, these below peaks actually changes according to the diameter of the ball. So about these points, the frequency gets decreased when we increase the diameter of the ball. As size of the ball gets larger, the frequency would go lower. And same as experiment 1, experiment 2 also shows no change in the sound intensity when we change the size of the ball. And the reason for this is same. Since we're wheeling the motor at the same angular velocity, there will be no change in the initial energy that the motor has. Therefore, there will be no change in the sound energy. So, there will be no difference in the sound intensity. And move on to my final experiment about the angular velocity. I used 3 different values of angular velocity, and this is how it changes. The blue one is for the waveform for 1200 RPM, and the green one is for the 1340 RPM waveform. As you can see, the graph shifts to the left, shifts to the right when we changes the angular velocity, when we increase the angular velocity. And also when we increase the angular velocity from the 1340 RPM to the 1520 RPM, it actually the graph shifts to the right, which means higher the angular velocity, the higher the frequency. And different from the experiment 1 and 2, the sound intensity also shows the increasing trend when we changes the angular velocity. So first about the analysis of the frequency. Since the increase in the angular velocity of the system will lead to the increase in the tension, therefore it will lead to the increase in the harmonic frequency. So we can make a conclusion that the velocity is proportional to the frequency of the generated sound. So about the sound intensity. Different from the experiment 1 and 2, actually we changes the angular velocity, which is our parameter. So angular velocity increases will lead to the increase in the initial energy. There will be the increase in the sound energy that will be transformed. So increase in the sound intensity. The overall conclusion is that the parameters that determine the pitch and the volume of the generated sound with their angular velocity, the diameter of the bow, and the diameter of the thread. And each parameter would have a relationship to the pitch and the volume of the generated sounds as follows. And this is the end of my presentation, and thank you.
Thank you for your inspiring presentation, the recording team. So you identified 3 sources of sound in your presentation. The first being the standing waves, second being the source created by the straw saw, and third being the frequency that's emitted by the ball. Now, out of these 3, can you tell me what is the most dominant source of sound out of those 3?
There will be the standing wave, but as I just mentioned in the motivation part, I said that the vortex made in the thread and the ball would make the resonance in the harmonic frequencies of the standing wave. So it would be the mean.
Is it possible to actually hear your sound sample that you recorded?
Hear my record sound?
Yes.
Do you want it?
Yes. While I'm asking questions, can you answer my question while the other members prepare the sound? So you mentioned the standing waves are actually the source of sound. So, well, in the case of standing waves, we actually see is that the vibrating, for example, in brain or a standing string, is vibrating at the exact frequency with the sound. So in case of whirling motion, do you think the frequency of the whirling motion equals the frequency of the sound that's actually emitted according to your theory of standing waves?
The vortex frequency equals the frequency of the generated sound. Your question is that?
Yes.
No. But it is not equal, but actually the vortex is the vibration of the air. Yeah, you agree on it? And the sound is actually the vibration of the air. Yeah? So, although it does not have an equal relationship between two, we can say that the increase in the vortex, the increase in the vibration of the air would increase the sound frequency.
I asked you about the frequency of the standing waves, not the frequency of the sound that is emitted by the vortexes that are created in the wake of the cylinder.
Pardon?
Okay.
We'll save later for discussion.
We would like to hear the sound you just said while they have 3 minutes to prepare.
This is the sound we recorded.
Thank you.
I'd like to start my refutation. So, good morning, ladies and gentlemen. My name is Hyung from Korean Media Leadership Academy, Team 혜움나래, and I'm here to present to you the opposition speech of problem number 2 of 2012 KYPT, Cutting the Air. So now let's briefly introduce the presentation overview of the reporter's side. The reporter's side started with the concept of what is sound, and then they mainly gave 3 sources of sound. First being the standing waves, second being the Kalman vortex sound, and third being the vortex behind the objects. And then they gave a theoretical background regarding the Reynolds number, and then they had an experiment about the horizontal whirling. And then the FFT program was used to find out the frequency of those beats. And the experiment was done regarding these 3 parameters: thickness of the thread, size of the ball, and the angular velocity. So their conclusion on their side was that the pitch and the volume is important, and overall the presentation lacked a connection between the fundamental explanations and the experimental tendency and data itself. Sorry for that. And so I'll briefly explain their fallacies. They lack fundamental explanations about what sound really is and how it's propagated through air pressure and vibrations. And then they lacked qualitative explanations about the tendencies in their graphs. So the graphs were not analyzed enough. Third, they lacked theoretical value and predictions upon the experimental data. So the actual predictions upon the experimental data and the frequency and theoretical data that they have obtained was not done. And finally, they had lack of explanations about what programs they used for the fast Fourier transformation process that they carried out. However, for prospects, she calmly explained about the key definitions of terms of the problem, so that was a good point for the reporter side. She confidently explained about the concept of Kalman vortex and standing waves. And she explained the general tendency according to different parameters. She said, first the thickness of the string, second angular velocity, and third the size of the ball. However, there were some missed points in her presentation. First being the most important thing: when you're analyzing a sound, you need to present a sampling rate. However, she did not do that. So I would like to ask her the sampling rate later in the discussion points. And the theoretical background for the straw saw was not given as well. There was a great misunderstanding about the standing waves in her presentation, and the frequency spectrum was misinterpreted as well. Finally, there was a really unclear explanation of sound intensity when she suddenly related the energy provided by the motor to the sound intensity itself. And finally, there was lack of repetitive experimentation, so we not really know if their data is credible. So now I'd like to move on to the discussion. So first, regarding the theory. So, reporter, you agree that the straw saw is the most fundamental and the basic equation in order to solve this problem, is that correct?
I mentioned the frequency of the vortex shedding.
Yes.
As you can see, B over the F D is equal to Stroh-Hall number.
Yes.
And I explained briefly about the Stroh-Hall's number.
So can you briefly tell me why the Stroh-Hall's number is valid,
Theoretically?
Yes.
Because I use the Stroh-Hall number to explain the vortex. Because the Stroh-Hall number is a dimensionless number to explain the motion of the turbulent
Using
flow.
basic concepts of displacement, velocity, forces, pressure, can you explain theoretically the Stroh-Hall's law?
Theoretically about the Stroh-Hall's law?
Yeah, so in short, can you prove the Stroh-Hall's law?
I mentioned the Stroh-Hall's law to explain my parameters, the relation to the generation of the sound.
So it was only done by references?
Yeah, I suggest some references.
I thought if that was done for her side, it would have been a much better presentation. And we'll move on to the next one. And second, for standing waves, what do you think causes standing waves?
Vibrating of the thread.
Right, for membranes and strings, you see that something's vibrating, and that vibration causes an air pressure difference,
Yes.
and that pressure and that wave propagates through our ear, that's supposed to vibrate our eardrums.
Yeah, that's the definition of the sound.
Yeah, no, that's the definition of standing waves. Now, however, in the whirling